Hello everyone, we are now on chapter 14, which is on regression and correlation. In this chapter, we will learn how to find relationships between two variables which are of a numerical data type. So it's going to be the study on two variables, but they will be of numerical or quantitative data. We'll be working with quantitative data. There'll be bivariate data. Bivariate means it'll involve two variables, and we are going to try to determine a relationship between the two variables x and y, and then we are going to see whether that relationship is meaningful or not. And we are going to establish, we are just going to focus for this course, we are just going to focus on what's called linear regression. That means when we map the two variables, they will give us an equation which will be the equation of a line, which we have studied previously in an algebra course, but we will now try to apply that to statistics. Now, in the first section of this chapter, we are going to review a little bit on linear equations with one independent variable. Now, we've all seen equations of this nature, right? Y equals mx plus b. So we may have been given in an algebra course before something like 1/3 x plus 7. This is just a made up equation, all right? And what this does is you can plug in any value for x and do this calculation. Plug in a value for x and complete this calculation and you will get a value for y. All right? Now, in that case, x, where we can plug in any value, any real number for x, and it produces a y value. In this case, the x value is called an independent variable because we can plug in any real number for x. So it's going to be called the independent variable. All right, but it's going to have one independent variable in the equations that we are going to study. And this is an example, y equals mx plus b is an example of an one independent variable. The other variable here, y, is called the dependent variable. All right, it's called a dependent variable. Why so? Because its value depends on what value we input into x, right? So keep in mind x will be regarded as the independent variable and y is the dependent variable. We learn next how to come up with linear equations. Previously, you may have been given a linear equations and you may have been asked to do different calculations. You may have been asked to find the y value given an x value. You may have been asked to write it in different forms. This is the slope intercept form, but you may have been asked to write it in point slope form or in general form, and also you may have worked on some word problems using these equations, right? Now we are going to learn in this chapter how to apply it in statistics, all right, and come up with an equation in the linear form. Here we talk about what we call the slope intercept form, but in statistics, we slightly change what we know as the slope intercept form and we call that the y-intercept and slope form. In other words, we'll call it the intercept slope form. Now, we had learned before that y is equal to mx plus b, right? That's the common form that we are taught in an algebra course. And M represents the slope of the line and B represents the y-intercept. What is an intercept? The y-intercept is a point on the y-axis. It's a point on the y-axis where the line crosses or intersects with the axis. The point where a straight line would intersect the y-axis is called the y-intercept of a line. All right, now this form, which is called the slope-intercept form, is normally written in y equals mx plus b, where m represents the slope and b represents the intercept. And that's how we learned in algebra. In statistics, it's going to be slightly different. It's still going to be about the slope and the intercept, but we are going to write it as y equals b sub 0 plus b sub 1 times x. So that what you see over here is this mx part moves to the right hand side, so it moves uh, we kind of interchange the slope part and the intercept part in statistics. That means the y-intercept comes first and the slope part is written later or after as the second term of the equation, right? Now, instead of m, we use b sub 1. So b sub 1 in this case is going to be our slope, and instead of referring to the y-intercept as just b, we write it as b sub 0. b sub 0 referring to the initial term, the term which does not have x in it. So that's going to be our y-intercept. So in statistics, uh, as we go through this course, we are going to write our linear equation in the form y equals intercept slope form. That means the y-intercept is going to come first it's going to be written as the first term of the linear equation, and then a plus sign followed by the term which has the slope, so b sub 1 times x. And remember, with the slope is also associated the variable, so the slope is the coefficient of x, right? Here, let's look at the graphs of different equations. Now, all linear equations will have straight lines for their graphs, and we are given here three different lines sloping in different directions, and they're all straight lines, right? So let's look at this line here. It has the equation y equals negative 3.44 plus 1.8x. Now, note this is not in mx plus b form, but this is in the form that we just learned in statistics of b sub 0 plus b sub 1x, right? So for this line, the slope is b sub 1, all right, which is 1.8. For this line, the slope, which we commonly have known so far as m, is now represented by b1. So b1, which again also represents m, has a value positive 1.8. Now, when the slope is positive, right, when the slope is positive, then the line will rise up from left to right. So the line slopes or rises from left to right. Look at this line here. It falls. It's a falling line. Let's look at the equation of this line. It says y equals negative 1.5 minus 2x. That means, right, let's use a different color. All right, negative 1.5 represents b sub 0 and b sub 1 is equal to negative 2. All right, keep in mind that the form is y equals b sub 0 plus b sub 1x. So if there is a negative sign in the equation, as in this case, then the negative becomes a part of b sub 1, because when you write it in the form of slope intercept, or intercept slope in this case, you're going to write it as y equals negative 1.5 plus negative 2x. All right, so negative 2 is going to be what? A part of b sub 1. So in that case, b sub 1 is a negative value, and whenever the slope is negative, the line will fall from the left hand side to the right hand side, right? And then we have this third line here, which is also a slanting line, but it goes up from the left to the right. However, it doesn't slope as steeply as this line here, correct? The slope, or it slants more gently, it rises more gently at a slower pace. Let's look at the equation for that. It's y equals 4 plus 0.2x. Now, because it's rising, even if it's rising slowly, it's still rising, its slope better be a positive slope, which it is. It's plus 0.2. That's the slope. And the y-intercept is 4. Now, again, what is y-intercept? Y-intercept is where the line crosses the y-axis. In this case, the line is indeed crossing the y-axis at 4. Correct? That's what b sub 0 is. For this line sloping up, also the first line that we looked at, all right, it crosses the y-axis at somewhere between negative 3 and negative 4. This is the point where it crosses the y-axis, correct? And it has negative 3.4 as its intercept, and that's where we see in the graph the line cuts the y-axis. And for this line, uh, the line which is sloping down, what is the y-intercept? It says negative 1.5, and as we see, the line is crossing the y-axis between negative 1 and negative 2, somewhere right at the center, which agrees with the equation, the y-intercept shown in the equation. All right, so this was a review of how the graphs look like and the relation it has with the slopes. All right. Here's a word problem applying linear equations. It's about word processing costs. It says a business service offers its clients word processing at a rate of $20 per hour plus a $25 disk charge. The total cost to a customer depends on the number of hours needed to complete the job. Find the equation that expresses the total cost in terms of the number of hours needed to complete the job. So in other words, we have to come up with an equation using the information given to us. Let's try to understand what this problem is about. It's saying that in order to get a word processing job done, the cost involves a flat fee of $25 for a disk, and then for every hour spent to do the work, they charge $20 per hour. Okay? So based on that, let's come up with an equation for it. So the total cost is going to represent our y variable, all right? The total cost is going to represent our y variable. And then remember the form again is y equals b sub 0 plus b sub 1 times x. So the slope part of the equation is going to be the last term, and the intercept part is going to be the first term. Now the intercept is or rather at the y-intercept, the x is 0. That means x doesn't exist. X does not have a value, or rather x has a value of 0 at the y-intercept. All right, at the y-intercept, x has a value of 0. That means it will represent the flat fee part of the cost. All right, so we have to begin the equation with y equals $25, where x does not come into play. All right, that represents our y-intercept where x does not come into play. And then plus, that's the form of the equation, plus for every hour it will cost $20. So if you spend $1, or if someone spends $1 on the job, it's going to be $20. If they spend $2 on the job, it's going to be 20 times 2, $40. If they spend 5 hours on the job, it's going to be 20 times 5. So what is going to vary is the number of hours somebody puts into the job, right? So that's going to represent x, and for every hour of x, it's going to cost $20. All right, $20. So this is how the equation is going to look like. Y equals $25 plus 20 times x. So at what rate will the cost increase? At the rate of $20 per hour. That's going to represent the slope. What is the slope? The slope represents the rate of change of a line or of any variable. All right, how fast or how slow, how rapidly or how slowly a line changes or a variable changes. All right, that's what the slope is about. So when we perform this calculation, we will get the total cost of the job. All right, the $25 is the flat fee for the discharge. For the $25, x does not come into play at all. It does not have anything to do with the number of hours. Even if somebody spends 0 hours on the job, they still have to pay $25 just for the disk, right? That's what it means. So here it says determine b sub 0. B sub 0 represents the intercept. So we are going to say it's going to be 25. And b sub 1 is going to be positive 20. All right, it's going to be positive 20. That means the line is going to rise. That means as x is going to increase, as the number of hours increase, the more hours you put in, the cost is going to increase as well. All right, so that's what this positive slope tells us. As x increases, y also increases. And then it says construct a table that gives the cost for jobs for the following hours. And this is already calculated. Hours represent x, so that's the input value. We go and plug in 5 into the equation. So to find the cost when the number of hours used is 5, it's going to be 25 plus 20. You plug in the 5 into x. So let's do that. We shouldn't write x. Let's replace that bit with 5. So y is going to be 25 plus 20 times 5 is 100. Therefore, the cost is going to be $125, and that's what they have here. Likewise, 7.5 is just have to plug in 7.5 into x and do the calculation and come up with a y value. All right, so that's how this is going to work for problems, application problems like this. Finally, let's talk a little bit about the slope. Again, it says here the graph of the linear equation y equals b sub 0 plus b sub 1 times x slopes upward if b sub 1 is greater than 0. We already talked about that. If our slope is a positive value, that means greater than 0, then the line will be rising from the left to the right. All right. If slope is a negative value, that means less than 0, the line will be falling from the left to the right, towards the right hand side. However, let's look at the line which is horizontal. All right, what happens to the horizontal line? A horizontal line will always have a slope equal to 0. And what that means is no matter what value x is, the y value will be a constant value. It will not change. For example, let's say this y-intercept is, I don't know, 2. All right, if it is 2, then at x equal to 0, it's going to be 2. If you look at x equals 1, all right, at x equals 1, it's also going to be 2. At x equals 2, it's also going to be 2. And on the negative side too, if you take x as negative 1, y is still positive 2 if you look at negative 2. And if you keep going for any value of x, the y is a constant value. That means x will not have any effect on y. And the slope is always 0. Now, another thing that I should remind you is the formula for the slope m, or now that we are learning b sub 1 is also a notation for slope in statistics. So I'm going to write both. The formula for the slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. All right, so that means if you're given 2 points on a line, all right, if you're given 2 points on a line, you can find the slope from those 2 points. How do you do that? Your first point will have a value of x1 minus, let's rewrite this, x1 comma y1. And let's say your second point is a point which we'll denote with x2 comma y2. So if you have those 2 points on a line, all you need to do is plug in y2, the second point's y value, into y2 minus the first point's y value divided by x2 minus x1. And what happens in a horizontal line is, since all the all the y values are constant, since the y values are all constant, no matter what the x values are, it'll always be the same y value we are subtracting. So for example, let's look at this point here, this point and this point. All right. The y values of both these points are 2, correct? So we'll end up doing 2 minus 2 in the numerator, but x can be anything, minus 2 minus positive 2. All right, so x value can be anything, doesn't matter. If the numerator is a 0, all right, if the numerator is a 0, the result will always be a 0. So that's how for a horizontal line, we always have a value for slope b sub 1 equal to 0. Now, keep that in mind because several sections later and also in chapter 15, when we do inferential studies, we are going to use this fact that the slope of a horizontal line is equal to 0, where x does not have any effect on the values of y. Right?
Now, in section 2 of this chapter, we talk about the regression equation, specifically how to come up with a regression equation from sample data. Now, in algebra, we are often given a specific linear equation and we are asked to do different things with it, maybe plug in an x value to come up with a y value or find the slope or change the form of the equation or work on a application problem using the linear equation and so on. In statistics, we start with a sample, right? We create a sample from our population, and then we have to collect the data, and then we have to analyze the data. So we always start with raw data in statistics. So we will learn how to come up with a regression equation from the raw data, right? That's the exercise we are going to go through in this particular section.
Now here we are going to talk about the scatter plot and try to understand what it is. Now keep in mind in statistics, we always start with raw data. All right, we define our population, we create a sample from it, then we send out surveys or collect our data from the sample and then start performing our descriptive study on the sample data. In algebra, when we work with linear equations, we were often given a linear equation and asked to do certain things with it, maybe find the slope of the equation or change the form of the equation or uh, work out a word problem applying linear equations, something like that. In statistics, we do not start with an equation. We start with raw data, and from there we try to establish or we try to come up with an equation. And before we even come up with that equation, we have to first figure out whether there is any relationship between the two variables we are studying. So in linear regression analysis, we are looking at two variables. There is the x variable and there is the y variable. So when we go around surveying, our survey will have two questions, all right? We'll be asking two questions, two related questions, so to speak, maybe. How many hours did you study for this particular test? And related to it is, what score did you get on that test? In that case, we are trying to find, we may be interested in trying to find if there's a relationship between the hours of study before a test and the score obtained on the test. Okay, so we have two questions, two related questions, so to speak, and we will try to establish a relationship between the two variables, and then if possible we'll come up with a linear equation from the data. All right, so initially we start with raw data and then we will come up with an equation if our data fits a linear model. All right, now since we start with data, randomly collected data, at that point we have no idea whether there's going to be any relationship between the data or not. So what we do is we just plot our data in a graph as a bunch of dots. And that's what is known as a scatter plot. A scatter plot is a graph of data from two quantitative variables of a population. Quantitative means numerical, so the data we collect for X and Y are numbers. They are not quantitative, they are not names, they are numbers, numerical data uh, of a population. And in a scatter plot, we use a horizontal axis for the observations of one variable and a vertical axis for the observations of the other variable. Each pair of observation is then plotted as a point. So the data that we collect is actually represented as an ordered pair. So we can have some data where a bunch of data rather, which is going to be represented as an ordered pair as x1 x sub 1 comma y sub 1 x sub 2 y sub 2, x sub 3, y sub 3. That's our raw data, our initial data. And we are going to see if these data points, all right, can be represented in a certain fashion, if there's a pattern to this raw data with which we can build an equation which is of the form, what was the linear form? It's y equals, not 0, so y equals b sub 0 plus b sub 1x. This is the form that we are going to use in statistics, which is a slight variation of the y equals mx plus b form that we were given in an algebra course, right? So what we do is, in a scatter plot, we have a y-axis where we plot our y variables, and then or where we are going to represent our y values. And then the horizontal axis will represent the x values, and each of these ordered pairs will be represented as points. We will graph those points, all right, bunch of points, and then we will see if there is a pattern to those points. If they can be represented as a straight line, it'll never be a perfect straight line because this is field data, this is raw data. However, if there is a noticeable pattern, then we can try to get a linear equation from our data. Okay. Now here's an example study from our book. It's on age and price of Orions. Orions is a fictitiously named um, car model, and what they're trying to do here is, the table below displays data on the age and price for a sample of 11 cars of the Orion model. Ages are in years and prices in hundreds of dollars. Construct a scatter plot for these age and price data. So what they've done is, they have taken a sample of 11 Orion cars. They had two questions in their survey, probably, or they were interested in two questions. One is, what is the age of the car? And number two is, what was the price, the selling price of that car for that specific age? And this is our raw data. So a 5-year-old car, for one sample, the 5-year-old car was sold for $8,500. Again, the price is in 100, even though they have represented this as 85, it should be interpreted as 8,500. All right. A 4-year-old car was sold for $10,300, so 103. They have taken the hundreds, all right, from here, and just represent, just to keep it simple. But always at the back of your mind, you must remember that these are 100. You don't sell a car these days for $85 unless it's to your family member or something, right? A 6-year-old car sold for $7,000, 7,000 or $7,000. Another 5-year-old car sold for 8,200, another 5-year for 8,900. So that's how the data should be interpreted. All right, we have age, which represents the X variable, and the selling price of the car, which represent the Y variable. So in ordered pairs, we can write this as 5, 85, then 4, 103. 6, 70. All right, first one being the X variable, and the second quantity uh, being the y variable. And the question says, construct the scatter plot for these age and price. So scatter plot is a graphic representation with a y-axis, a vertical axis, where we will represent the y values, and the x-axis, the horizontal axis, is the x-axis, where we will represent the ages. So perhaps start from 1, 2, 3, 4, and so on, 4, 5, and so on. And our y-axis will be, what's the lowest value? Let's make this uh, we'll start maybe from 20, 40, 60, all right, 80, and so on. Again, this is all in hundreds. All right, so I will show in the next slide how they have come up with, how they have plotted the each of these ordered pairs and what the scatter plot looks like. So, but over here I just showed you the graphic, the rather the coordinate plane, all right, where we are going to represent our data. Vertical axis, the y values are represented, the horizontal axis, the x values, in this case age and price. All right. Now as you can see here, this is the scatter plot for the example we just looked at. Along the horizontal axis are the values of the different values for the age, starting from 1 to 8. And for the vertical axis, the y values, we've shown them along the vertical axis, the price in hundreds, and we've broken them up by as in intervals of 10, right? 10 all the way to 180. And we have plotted the individual data points on this graph, on this plane, and they represent a particular age. Each dot represents a particular age and the corresponding price. All right, so a 4-year-old car, we go from an X value of 4 all the way up to, it was 10,300, so it should be a value between 100 and 110. And this dot here, this plot is right there, right? So if we, let's do this, if we draw a line up to the point and then a horizontal line all the way to the y-axis. All right, I think it was 103, so this point is 4 comma 103. All right, so that's why it's a value between 100 and 110. All right, so we have a bunch of dots here. We now have to see whether there is a pattern to it. All right, and even though it's kind of over the place, it's not a perfectly arranged uh, line, it's not laid out in a perfectly arranged line, we can perhaps force a line. So if I remove this, it seems it's possible that we can draw a line, something like this, all right? Or maybe a line which goes like this through many of the points. Oops. We can force different lines, all right? Maybe another one which could go like this and cover most of the points. So subsequently, we are going to study out of these 3 lines here, which would be the more appropriate line to choose, all right? So that's what we are going to go into in the next few slides, because we can force different lines, all right, as many lines as we want, thinking that, oh, this may be a better fit, all right, than the previous one. But how can we mathematically show that the line that we chose is the one of the best fit? All right, so that's what we are going to go into next. Now, to decide on the line of best fit, we are going to work with a different example, a simpler one here, just with 3 data points. But just to recap, in the previous slide, we said that we could force different lines through our scatter plot, and then we have to decide which one is the line of best fit and choose the equation related to that particular line. So here the data that's given to us are 1, 3, 2, 1, and 3, 5, and these are the points, the scatter plot related to this data. And as you can see, we can draw different lines through this. We can choose this line, or we can force another line, which is, well, that's not a pretty good line. Um, Maybe something that goes like this, or another one which goes like this, right? We can draw multiple lines through this scatter plot, right? But we can only choose one. Which one of these do we choose? So there's a mathematical way of coming to a conclusion on that, which we are going to see in the next slide. So here we have chosen 2 lines fitting our data point, those 3 data points that we showed previously. So one data point was here, the other green point dot is here, and then one here. The same data points represented on the second graph, and then we have 2 different lines that we forced through these data points. All right. So how do we figure out which one is a better fit? What we do is we see that we look at points on the line that we forced, all right, on these blue lines, all right. So we have here at 1, there is a point that would lie on the line, all right, and that point would come from the equation, the linear equation associated with this line, all right. So if we plugged in uh, a value of 1 for x into this equation, which is y equals -1 plus 2 times 1, all right, we plug in 1 for x, we'll come up with -1 plus 2, which would give us a value of 1, all right. That value would lie on the, all right, on the line. All right. Now this green point here, this green dot, which also has an x value of 1, is an actual data point. It's our sample data. What we do is we try to find out what is the variance of the predicted value that comes from this line. All right, what is its variance from the actual data? How far is the predicted value off from the actual value? And that variance we refer to as E, also called error. All right, we refer to as error. All right, and then once we find all these differences between the actual value and the predicted value coming from the line, we put them in a table, we square them, we sum them up, and whichever of these lines have the least error, least error squared, in other words, will be our line of choice. All right, and this whole process is also called the least squares criterion, because we end up choosing the line that satisfy or that meets this criterion of having the least squares. We'll go through a step-by-step process of finding that least squares, or working that least squares, in the next couple of slides. So here we have our two line equations. We call the first line line A and the second line line B. And what we have there associated uh, equations for each. All right. For line A, it's y equals negative 1 plus 2x. For line B, it's y equals 1 plus x. And then we create two tables. The first one has all the x values from our data and then all the y values from our data, and they should be identical for both the lines, for in both the tables. uh, X and Y values should remain the same. All right, it should be the same data that we are working with. What should be different are the predicted Y values. Now, the predicted Y values we indicate with Y hat. We put this hat over it to indicate predicted values, and those predicted values come from the equation, from this equation. All right, so what we do is we take out each x value, plug it into the equation, and come up with the corresponding y value and write it down here, right? Again, y hat represents predicted y values. Predicted y values obtained from the equation. Obtained from the given equation of the line. So in the fourth column, we have something called E. So E represents error. All right. E represents error. And what is error? Error is the difference between the actual Y value and the obtained Y value or the predicted Y value. So E basically represents Y minus Y bar. Sorry, Y hat, not Y bar. Y bar is completely different. All right, Y minus Y hat. So 3 minus 1 is 2. 1 minus 3 is negative 2, and 5 minus 5 is 0. So those are our E values, error values. However, we have to square them in the next column. So 2 squared is 4, negative 2 whole squared is 4, and 0 squared is 0. We sum them up. So this value 8 is the sum of E squared. Sum of E squared. We do the same thing with the line with line B, whose equation is y equals 1 plus x. We first write all our x and y values in the first two columns. We obtain our y hat values, but this time we use this equation for line B. So we plug in 1 into x, and 1 plus 1 is 2, and that's how we got the 2. All right, for the next one, x is 2, so plug in 2 into this formula equation. 1 plus 2 is a 3. We write the 3 here. So that's how we get our y hat values. In the next step, subtract y hat from y, and that's our E or error. So 3 minus 2 is a 1, 1 minus 3 is a negative 2, 5 minus 4 is a positive 1. In the last column, just square them all up and add them, and all right, sigma E squared. And once we have both our sigma E squared value, we choose the one with the smaller value. All right, so this one has an E squared value. Sum of E squared value is 6. The other one has a sum of E squared value as 8. Pick the one which has the smaller value, smaller errors, smaller sum of errors. In other words, that's going to be a better fitted line. Now this slide explains a little bit on the steps we took previously. It's the same. These two tables are the same what we saw in the previous slide. It says to determine which line fits better, we compute the sum of the squared errors, that is sigma e squared sub I. The line having the smaller sums of squared error fits the data better, right? So sigma e squared is represents the sum of the e squared, the individual e squared values in the last column, and the line with the smaller sum of squared errors fits the data better, so we decided on choosing line B, which has the equation y equals 1 plus x, because the errors, that means the difference between the predicted values and the actual values uh, are smaller, the differences. So among all the lines, the least squares criterion is that the line having the smallest sum of squared errors is the best fit. Now this defines the least squares criterion one more time. It says the least squares criterion is that the line that best fits a set of data points is the one having the smallest possible sum of squared errors, and the line that best fits a set of data points is, according to that particular criterion, least squares criterion, is called the regression line, while the equation, the related equation, is called the regression equation. Now we are ready to talk about how to come up with a regression equation, the slope and the y-intercept. All right, so we'll talk about the formulas that will give us the value of the slope and the value of the intercept from our data set. However, before going into that, we'll talk about some quantities which you will see in the formulas for the slope as well as for the intercept. All right, and those quantities are s sub xx, s sub xy, and s sub yy. Let's quickly talk a little bit about what they represent. S sub xx is how much it kind of quantifies how much each individual x values vary from the overall mean of all the x values. So we see here it's a sigma, and then within brackets we have x sub I. X sub I represents the individual x values, and here we have minus x bar, and x bar is the mean of all the x values. So essentially when we say x sub I minus x bar, we are referring to how much each individual x value is off from the mean of all the x's, and then we square them and sum them. All right, and that's the defining formula of S sub xx. Now, these defining formulas are also backed up by a computing formula which does the same thing. The result using the computing formula is going to be the same as that of the defining formula. The only difference is that computing formula is a faster formula and more efficient. So if we have a large data set, then we are better off using the computing formula because we can find the calculation far quickly than we can with the defining formula. All right, what is S sub xy? S sub xy, as you will note, is the joint variation between the x and the y value. So it means it checks how much each individual x value varies from the mean of all the x values, as well as how much the y values, individual y values, are off from the mean of all the y values, and we multiply them and then we sum them up. S sub yy is just focused on the y values, how much an individual y value in our data set is off from the mean or average of all the y values, we square them and we sum them up. So S sub yy is pretty much the same as what S sub xx is doing. Only thing is that S sub xx is for the x values and S sub yy is for the y values. And each of these have a corresponding computing formula. And like I said, for your tests and assignments, most likely we will be using the computing formula because you'll find it much faster. But we will work on some exercises using the defining formula. The defining formula helps us understand what's really going on. All right, it defines, or it's based on the definition of these quantities. All right, so next we will go into some uh, equations which will give us the value of b sub 1, which is the slope of the regression equation. And after we find b sub 1, we should be able to come up with a b sub 0 value, which is the y-intercept, and then come put together the regression equation. So here we have the formula for b sub 1, and that's s sub xy divided by s sub xx. Now, when working on the regression equation, we must first find the slope and only then we can find the intercept. All right, because as you can see in the formula for b sub 0, we are using b sub 1. All right, now b sub 0 has two formulas really. The first one is the defining formula and the second one is the computing formula. So we'll work on an example using these. So these two equations give the slope and y-intercept of the regression line respectively. So one more time, we have the different formulas for the regression equation. This is more zoomed in, so let's see. It's easier to read now. Y hat equals b sub 0 plus b sub 1x is the formula for the sample regression equation. So whenever you see a y with a hat on it, that means we are referring to the regression equation, all right, which is the sample regression equation, not the population regression equation. The population regression equation will just have a y on it and it won't have small b, the lowercase b. It will have beta, the Greek letter beta. We'll talk about that later. Now the formula for b sub 1, which is the slope of the equation, goes with the formula s sub xy divided by s sub xx. And we know each of these have their own formula, the defining formula or the computing formula, but we will work on an example using the computing formula, and most of the time I encourage you to use the computing formula unless you have a very small data set. All right, but we'll work some examples using the defining formula as well. B sub 0, which is the y-intercept, goes by this formula here. This is the defining formula and here is the computing formula. However, to find b sub 0, we first need to find b sub 1 because as you can see, the formula does use b sub 1 when for the y-intercept. All right. Now here's the example problem on Orion cars, which we introduced before. We have here in this table the age of 11 a sample of 11 cars are presented here with their ages, and the Y value represents the price of each car by their age, the selling price of each car. So X represents the age in year, and Y represents the price in hundreds. Now that's very important. You have to keep that in mind when you are especially interpreting these problems. All right, you cannot say that a 5-year-old car sold for $85. You have to factor in the hundred. So it's a 5-year-old car sold for $8,500. A 4-year car sold for $10,300, 6-year old sold for $7,000, and so on. All right, so don't forget the units, all right, the how it is to be written, especially when interpreting it. Now I'm going to use the computing formula to find the slope, and then the same computing formula to find b sub 0, because we can work that out far quickly and we do not need uh, more columns. All right, we can work out with a minimum number of columns if we use the computing formula. So this is a formula which is sigma x times y minus sigma x times sigma y divided by n over S sub x, x is sigma x squared minus sigma x whole squared divided by n. All right, so to plug in the values into this formula, we essentially need just two more columns in this table. One is to calculate x times y, which we are going to plug in here, right, for sigma xy, and another one to find x squared, which we are going to plug in here. And for sigma x and sigma y and sigma x whole squared, we have to just sum up our age values and the price. So we are going to work through it. All right, so just follow me along. What I did here is I multiplied in this column xy. I created a third column called x times y, and I multiplied the x and the y values and noted down here. All right, for every row, for every car. So 5 times 85, 425, 4 times 103 was 412, and so on. And then I sum them up. This last column is the total, or the sigma column, right? So this one is sigma x, this one is sigma y, this one is sigma xy, right? Sigma xy. And this last one is sigma x squared. All right, so just multiply your x and y values and sum them up, and make sure you are plugging in the values in your calculator correctly and getting the right total. All right, and then for the last column, all you need to do is square all the x values. So 5 squared 25, 4 squared 16, 6 squared 36, 5 squared 25. All right, so square all these individual x values and sum them up, which comes to 326. Right, and then we need to sum up all the columns. So sum of all the ages is 58. Sum of all the y values is 975. Sum of x times y is 4732, 4732. And sum of all the x squared values is 326. All right, now let's see what we plug in where in this equation. The first one says sigma x times y. Sigma x times y is here. Now don't let this sub i's bother you. That is the notation which we normally present in a formal way. But sigma x sub I times y sub I, this I represents the individual x values. All right, we can just ignore them and just write them as sigma x times y. So we are going to plug in 4732 into the first term of the numerator, and that's what I have here. All right, then it's sigma x, that means the sum of all the x values, which was 58. So I wrote 58 times the sum of all the y values. So the sum of all the y values was 975, and I have 975 here. Replace sigma y by 975 divided by n is 11, correct? So we have 11 uh, uh, 11 data points. All right, that's our sample size. So divided by 11. Now in the denominator, it's sigma x squared. That is the sum of all the x squared values, which is 326. And that's why I have a 326 here, minus sigma x whole squared. That means I'm taking my 58 and squaring it and then dividing by n, which is 11. All right. And when you do this calculation, we come up with a value of negative 20.26. All right. So that's our slope. This is our slope. So we have a negative slope here. That means we will have a line which slopes down to the right from it slopes down from left to the right. And if you remember the graph of this the scatter plot and of this data that we came up with in the beginning, it was trending down. As x values were increasing, the y values were trending downwards. All right, so we got a value for our slope. We now have to find a value for the intercept. And again, we are using the this computing formula, which is 1 divided by n times sigma y. Sigma y is the sum of all the y values. So I'll have 975 minus, all right, minus, we have to plug in whatever we found for the slope, which is minus 20.26 times sigma x. So sigma x is 58. So let me do this. Okay, so 58, this bracket closes the bracket before 975. All right, for a second I got confused with this extra bracket. So 1 divided by 11, 1 divided by n is 1 divided by 11 times 975, which is sigma y. All right, minus 20.26, which is b sub 1 times sigma x, which is 58. And this calculation comes up to 195.47. So now we can just plug in the values of the intercept and the slope into the form of the regression equation and come up with an equation which is y hat equals 195.47, which is the y-intercept, minus 20.26x. So our slope here is, our slope is b sub 1 is negative 20.26. Our intercept is 195.47. Now, what does this mean? All right. This intercept tells us that when the age of the car is 0 years, for a car that's 0 years old, we can expect the selling price to be $19,547. All right, again, you have to factor in the price in hundreds. You cannot say that a 0-year-old car, a brand new car, essentially costs $195. That's not correct. All right, it's 195.47 means 19,547. You have to add those extra zeros from the hundreds. And the slope tells us that for every year increase in age, the price of the car is going to fall by $2,026, right? The price of the car decreases by $2,026, and this negative slope tells us it decreases. The price decreases as age increases. The price of the car is decreasing. Uh, it's getting cheaper. All right, it's depreciating, so to speak. Okay, so this is the example worked out, and this example actually is in the textbook. You can also read that up there. All right. So here is the graph of the line we just found, which is y hat equals 195.47 minus 20.26x. And you see over here, even though the line does not really pass through any of the actual data points, but the data points, all right, the actual values are pretty close to that line. All right, and some of these uh, points are actually touching, almost touching um, the regression line. All right, so this line was drawn from this regression equation. It's called the regression line. This one is called the sample regression equation, and we see it against the actual scatter plot, and we find that they are pretty close. This is a pretty fitted line. All right. Now, two new terminologies are going to be introduced at this point. One is called the response variable, and the other one is called the predictor variable. Now, previously we talked about the dependent variable and the independent variable, isn't it? Independent variable, and we said that our x value is our independent variable because we can plug in any real number for x. It's called the independent variable, and the dependent variable was y. It was called dependent because it depended on what value we were inputting for x into our equation. All right, it was a result, it was a function of whatever we were plugging in, whatever value we were plugging in for x, but x could take any real value. Now, the response variable is the variable to be measured or observed. Now, in statistics, we call it response variable and predictor variable. Response variable is what we want to measure. All right, the output that we get from the equation. So response variable is going to be our y variable. So response variable is the output variable. And what is the output we get from our equation? It's a y value. So output variable, so it's a y variable. Predictor variable, on the other hand, is used to predict or explain the values of the response variable. And the predictor variable is the x value, the input value, or rather input variable. Right, the input variable is x, so it's the x variable. Now we will be using these terms quite frequently in the rest of this chapter, as well as in chapter 15. So just keep that in your mind, what the response variable is referring to. The response variable, whenever we use that term, is the y variable, and the predictor variable, the variable that we use to predict the y value, is called is the x variable. All right. Now, very quickly, we are going to talk about another term in statistics and especially regression analysis. It's called extrapolation. What is extrapolation? Now, previously with the actual data, we had our x variables, x values between 2 and 7. All right, we didn't have in our actual data set, we didn't have a value of x for 1. Anything less than 2 was not in our actual data set. Neither did we have anything beyond 7. I think um, the highest x value we had in our data set was 7. Right? Now, when we have our regression equation, when we create a regression equation, come up with it, we can use it to plug in any value for x. All right, even if it was not in the actual data set. All right, we could have plugged in 8, we could have plugged in a 9-year-old car, we could have plugged in 11 a value of 11 for X to see how much the selling price of 11-year-old Orion would be. All right. So that process of plugging in values outside of the actual data set into the regression equation and coming up with predicted Y values is called extrapolation. So that's why you see dotted lines. All right, we can extend this regression equation line, this regression line for values which are outside of the data set, for values that were not included when creating the regression equation, right? Now we'll talk about what is generally called an influential observation. Sometimes in our data set, we may find what is called an extreme value or an outlier. That means that particular value, the data point, is or does not fit the general trend of the other data points. All right, it's considered to be an outlier, an extreme value. Now, if we decide to remove that extreme value, that outlier, and regenerate our equation and therefore our line, regression line, we may see that it's a pretty different line from what we got when we included that outlier in our data set and did our calculations. All right, so that's what they have done here. This blue line over here is the line of the sample regression equation that we came up with, which was 195.47 minus 20.26x. That's based on all the data. And then they decided to remove this extreme value and they regenerated the equation, and it was a completely different equation. Y hat equals 160.33 minus 14.24x. So the slope changed, the intercept changed as well. All right, so this happens often with influential observations that are removed from data set, but we sometimes have to remove it if we see that that's a pretty obvious outlier. Okay. Now in section 3 of chapter 14, we are going to talk about the coefficient of determination and another coefficient in chapter 14.4, which is going to be called the correlation coefficient. So these are two different measurements or two additional measurements done on the regression equation. Now the first one, coefficient of determination, that we are going to discuss in the next few slides is going to tell us how valuable that regression equation is in making predictions. All right, that's what the coefficient of determination, it's a measure, and based looking at that measure, that quantity of coefficient determination, we can tell whether the equation is a good predictor of the Y values. The correlation coefficient will tell us how strongly the X and Y values are correlated. All right, so we'll talk about the correlation coefficient in the next section, but we'll first go into understanding what the determination coefficient of determination is. Now to come up with an equation for the coefficient of determination, we have to look at certain quantities. Now some of these quantities will seem familiar to you because we talked about this, we used these quantities when we were doing the ANOVA testing, right? Uh, so let's look at how these sums of squares apply to regression. The first one is total sum of squares, called SST. It's the total variation in the observed values of the response variable. Remember, we just talked about the response and the predictor variable. The response variable represents the y values. So SST is how much the individual y values are off from the mean of all the y values, and then we square them and sum them, which makes it the total sum of squares. All right, but it is the squares of the y values. It deals with the response variable. The other one is the regression sum of squares, or SSR. The variation in the observed values of the response variable explained by the regression. SSR goes by this formula. Well, let's see, or let's try to understand what we are doing here. We had y hat sub I. Remember, this y hat is a part of our sample regression equation. Our sample regression equation looks like this. Y hat equals b sub 0 plus b sub 1 times x, correct? So y hat represents the regression, um, the predicted values coming from the regression equation. And what we are observing, what we are calculating here is how much the predicted y values are off from the mean of all the y values, the actual y data values. Right? So it's the difference between the predicted values and the mean y observed y values, y bar. And then of course we square it and sum it. It's called the regression sum of squares, regression sum of squares, SSR. Finally, we have the error sum of squares, which is SSE, and this is very similar to the E squared formula, which we learned in when talking about the least squares criterion. It's the variation in the observed values of the response variable not explained by the regression. So SSE represents, this is the formula for it, it's how much the individual y values, the actual individual y values, differ from the predicted y value. So it's the gap between the actual data, actual y values, and the predicted y values that come up from the line. And of course, we square them and sum them. It's called the error sum of squares. This is the same formula we used when we were trying to work through the least squares criterion, all right, towards the beginning of this presentation. Now, keeping those sum of squares definitions and formulas at the back of our mind, let's just talk about what the coefficient of determination actually means. The coefficient of determination is a measure that determines how valuable the regression equation is in making predictions, whether it is the equation itself, the regression equation itself is a good predictor of the y values. One method is to determine the percentage of variation in the observed values of the response variable that is explained by the predictor variables. What is the predictor variables? The x values, correct? Response variables represent the y values and the predictor variables are the x values. So using the formula of the coefficient of determination, we will come up with a proportion value, a quantity which we can translate into percentage, and that percentage is really the variation in the observed values of the response variable explained by the predictor variables. Now we just talked about the percentage of variation and we called it the coefficient of determination. But how do we calculate the percentage of variation? In order to calculate that, we will need two quantities. One is the SSR and the other one is the SST. The SST is the total variation in the observed values of the response variable. And therefore this is the formula. We already talked about it, so I'm going to just skip through it now. But we need the SST, which is the total sum of squares, and we also need the SSR, which is the regression sum of squares. And what is SSR? It's the amount of variation in the observed values of the y variable. Response variable means y variable, as explained by the regression equation. So how much the uh, predicted values vary from the average y values, which represents the mean of the y values in the actual data. We have a third quantity which is called the error sum of squares, but we don't need this to find the uh, coefficient of determination. Actually, it's not a part of the formula for it, but we will need it for something else pretty soon. So let's just review it, remind ourselves what it is. It's SSE is the error sum of squares. It's the variation in the observed values of the response variable not explained by the regression equation. All right. So sigma, it's the sum of the how the actual data values vary from the predicted values. We square them and sum them. That's the error sum of squares. Finally, we come to the equation or the formula for coefficient of determination. Now the notation for coefficient of determination is r squared. All right, we put a square, and then the the notation we use is r squared. So using SSR, regression sum of squares, and SST, total sum of squares, we can calculate the coefficient of determination r squared. So this is the formula for it. It's SSR over SST. It's the ratio of the regression sum of squares and the total sum of squares, and it gives a value between 0 and 1. All right, so r squared, because it's squared, it can never be a negative value. It's essentially a value between, r squared is between 0 and 1. It cannot be greater than 0. It cannot be a negative value, right? But this is the formula to use, and in order to come up with an r squared value, we need a value for SSR and SST. The coefficient of determination r squared lies between 0 and 1. It's a quantity between 0 and 1. So we usually get it as a decimal value between 0 and 1. A value near 0 suggests that the equation is not very useful for making predictions. If it is close to 0, that means it's useless as a predictor of y. Uh, a value near 1 suggests the equation is quite useful for making prediction. In fact, the closer it is to 1, the more useful it is. It's a perfect equation, but if it is closer to 0, that means it's a poor predictor. And if it is in between 0 and 1, maybe 0.5 or 0.6, that means it's moderately useful in making predictions. So in order to recap, the coefficient of determination is a descriptive measure of how useful the regression equation is for making predictions. It's denoted by the uh, letter r. So it's r squared, all right? Not just r, it has to have that square on it. If you just write r, then it refers to a different measure which we'll learn later on. So r squared denotes the coefficient of determination. It's the proportion of variation in the observed values of the response variable. Again, response variable means the y variable. So the proportion of variation in the observed values of the y variables explained by the regression. The formula for it is SSR over SST, and in the next couple of slides, we will go through a simple example of how to calculate the r squared using the defining formula. And then later on in one of the worksheets, we will go through the process of using the computing formula, which is way faster than the a defining formula if we have to work with a large volume of data. So here is the simple example that we were talking about. We worked with this before when finding the least squares, when applying the least squares criterion. So it's the same data set. In the first column, we have the x and y values that were given to us, 1, 3, 2, 1, 3, 5. These are the ordered pairs. And then we have the values for the predicted y values, which came from a certain equation. It was given to us, but it's not on the slide, but there was an equation associated with it, and we got these values for y hat 2, 3, 4 by plugging in the x values into the equation. All right. And then we find y minus y bar. So we had to calculate the mean of the y values. So the mean of the y values, let's do that quickly here. What is the mean of y values? Y bar is sigma y over n, right? So the sum of all the y values, 5 plus 3, 8 plus 1, 9. So 9 over 3 is a 3, correct? So y bar is 3, and we have to go and subtract that value from each of these individual y values. So 3 minus 3 is 0, 1 minus 3 is negative 2, and 5 minus 3 is a positive 2. In the next column, we are squaring all of them because eventually we have to sum them, right? So 0 squared is 0 minus 2 whole squared. And the minus also gets squared. So we have a positive 4, and then 2 squared is a 4. We sum them up, and that's going to be our SST. If you recall, the formula for SST is sigma y minus y bar whole squared. All right, that's the formula for SST, and we perform that through the table. All right, and we got a value of 8. Now, what was the formula for SSR? The formula for SSR was sigma y hat minus y bar squared. Okay, so let's see how we work through that. So over here we had y hat minus y bar. Again, what is y bar? Y bar is a 3, correct? We calculated that here. So so it's y hat minus 3. So 2 minus 3 is a negative 1. 3 minus 3 is a 0. 4 minus 3 is a 1. We have to square them, each of these values. So negative 1 squared is 1. 0 squared is 0. 1 squared is 1. We sum them up and we get a value of 2. And that's our SSR. So our SSR is a 2. So to find R squared, all we need to do is divide SSR by SST, and we should come up with a value of 2 over 8, which is 1/4 or 0.25. That's the coefficient of determination. Now, the other columns are to calculate SSE, right? SSE is the actual y values minus the predicted values. All right, it's the same. So let me write that down here. These two columns are to calculate SSE. The previous two columns were to calculate SSR, and these two were to calculate SST. Now we don't need to find SSE in order to find R squared, the coefficient of determination, but while we are at it, let's just do it anyway. So y minus y hat is 3 minus 2, y minus y hat. So 3 minus 2 is a 1, 1 minus 3 is a negative 2, and 5 minus 4 is a 1. We have to square them again. So 1 squared is 1, negative 2 squared is 4, 1 squared is 1. Sum them up. That's it comes to a value of 6, and that's your SSE, SSR, and SST. Now, like we saw in the ANOVA testing where we found not the SSR, it was SSTR at that time. Uh, there is a what is it called? A theorem, all right, which says SST, all right, just a second, SST is equal to SSR plus SSE, all right? It will always be like that. It's an established fact. So let's see if that is true or not in this case. SSR was a 2, SSE was a 6. So 6 plus 2 is equal to 8. So we have tested, verified this fact that SST equals SSR plus SSE. So here's the regression identity that we just spoke about. The total sum of squares equals the regression sum of squares plus the error sum of squares, denoted by this equation here, SST equals SSR plus SSE. So if we found SST, if we found SSR, we don't even need to do the calculations for SSE through the table. All right, we don't have to do y minus y hat and all that. We can just solve for this equation. So if SST, all right, if SST we know is 8 and SSR is a 2, and all we do is we solve this equation for SSE. So SSE would be 8 minus 2, which is a 6. All right, 8 minus 2 equals 6. And that's what we got after we did the calculation through that table as well. So what I'm saying is if we know this identity, then we can avoid some extra work to find SSE. Now, before wrapping up this section, let's work on one problem using the computing formula to find uh, the r squared value, the coefficient of determination, right? So here are the formulas. Again, keep in mind r squared is equal to SSR over SST, and the uh, computing formulas for SST and SSR are given here. Now we are going to use the example of the Orion cars to find its r squared value. So in the next slide, we'll see the data and let's do the calculation using these formulas. All right. So we'll work on this example to find our r squared value, but I'm going to write the formula here for the SST and SSR, the computing formulas this time, right? So I'm going to write here SST, hold on one second, SST is equal to, this is a computing formula, it's sigma y squared. It's all with y's for the SST. So sigma y squared minus sigma y whole squared, right, divided by n. All right, so that is the formula for SST. For SSR, right, for SSR, this is how the formula looks like. It's sigma x times y, all right, x times y minus sigma x times sigma y divided by n, and this whole numerator is squared, okay, divided by sigma x squared. It's actually whatever the SST is, except that instead of y, we use x. So sigma x squared, instead of sigma y squared, we write sigma x squared in the denominator for SSR, minus sigma x whole squared divided by n. All right, so if you can build a relationship, a link kind of between the different formulas, it's much easier for you to remember. All right, so in the denominator for SSR, we have the exact formula as in SST, but the only difference is instead of Y, we have X. All right, we work with X. So now let's apply the formulas to come up with a value for SSR, because the final calculation for R squared is very simple if you know the values of SSR and SST, correct? It's SSR over SST. So let's plug in the values for SSR. SSR is sigma x times y. So what we did here in our uh, in this table, we multiplied x and y, which we did anyway to build our equation, the regression equations. We had a column for x, y, x times y, where we multiplied the x and the y values and summed them up and got a value 4732. And then in the next column, we squared all our x values and added them up and came up with a value of 326. But we need another column for the coefficient of determination for the R squared value to find the SST, and that's the Y squared value. So we do have to go and square up all these Y values and write it in the last column, the squared values in the last column, and sum them up, and we came up with a value of 96,129. All right, so now we can just work with the summation columns, the last total column. So sigma x times y is 4732, right? It's the total column of the xy. So 4732, 4732. And then we have here sigma x times sigma y. So sigma x is 58. We have to put a minus in between. So minus 58 times sigma y is 975. 975 divided by n is 11. But we have to square this entire numerator. And then in the denominator, we have sigma x squared, correct? It's sigma x squared. So let's pick our x squared total sum sigma x squared value. That's 326. 326 minus sigma x whole squared. So 58 whole squared divided by 11. And when we complete this calculation, we should come up with an SSR value of 8285, 8285.80. All right, so you can do this calculation on your calculators and verify if the answer is indeed 8285.80. But this is how you plug in the values. An important thing is, don't forget that the numerator in the SSR has to be squared. Sometimes we miss that. All right, don't make that mistake. You have to square because it's, after all, it's R squared, isn't it? This is R squared. So make sure there must be a square somewhere in the equation set. For SST, to calculate SST, all right, it's sigma y squared. So sigma y squared is 96,129. So 96,129 minus sigma y is 975, this value here, 975. So I'm going to write that 975 squared divided by 11. All right, and when we complete this calculation, we should come up with an SST value of 9708.54. 9708.54. So here we have our SST and SSR values just plug them into the formula for r squared. So r squared is going to be 8285.8 divided by 9708.54. All right. So our r squared value, and I'm going to go from here, I'm going to, just because of lack of space, let's do the work here. R squared is, what is it? 0.8535. This is the value for the coefficient of determination. So it has to be a value, keep in mind, it has to be a value between 0 and 1, and this is close to 1. So that means this tells us that the equation, the regression equation we found, is a pretty useful equation. All right, the closer it is to 1, that means it's rather useful, all right, for making predictions. We'll be finishing up chapter 14 by learning another descriptive measure of regression, and that's called linear correlation. Previously, we talked about the correlation or the coefficient of determination, which was denoted by the symbol r squared, correct? That was the coefficient of determination. Now we are going to talk about the linear correlation, also called the correlation coefficient. All right. Now this matrix is denoted by the letter R without the square. All right. So linear correlation coefficient is denoted by the letter R, and this particular measure tells us how well x and y variables relate with each other. That's why correlation. So how well the x and y variables relate with each other. Now they could relate positively. That means as x goes up, as x values go up, the y values also increase. Or it could be negatively correlated. That means if the x values increase, the y values decrease. In both cases, they are correlated, right? In different directions, but they are still correlated, and there could be a situation where they are not correlated at all. So this measure is going to tell us, first of all, if they are correlated or not, and then it's also going to tell us if they are correlated indeed, then whether they are positively correlated or they are negatively correlated, and or they are not strongly correlated at all. All right, they are weakly correlated. All right. Now, we will also learn that, or we will also realize that this linear correlation coefficient also ties up with the slope of our regression equation in some ways. All right. So let's go into the details of these in the next few slides, and then we will work on calculating the R value, the correlation coefficient value on that Orion car model uh, example. All right. Now let's go into understanding what linear correlation coefficient means. It says here the linear correlation coefficient is a descriptive measure of the strength and direction of the linear or straight line relationship between two variables. So the two variables referred to here are the x and y variables, right? So this is a measure that will help us determine how well the x and y variables are related to each other or correlated. And not only that, it tells us how strongly they are related, as well as the direction of that relationship. That means direction would mean uh, the two variables would be considered positively correlated if we have a line that rises from the left to the right. All right. And then if would be negatively correlated if it was a line which drops from the left to the right. It's a falling line. All right. So uh, it can be x and y variables could be positively related, correlated, or negatively correlated. Both are still, even though the directions are different, they are still correlated. And it also tells us how strongly they are correlated, they relate to each other. Now here it says the measure is denoted by the letter R. We spoke about that before. Keep in mind the correlation coefficient is denoted by R without a square. If it's a square, it's a different measure. It's a coefficient of determination measure, which we learned in section 3 of this chapter. Okay, for to denote correlation coefficient, you have to use the symbol R, and that value, that measure lies between -1 and 1. Now, if it is negative, close to, or rather, uh, let me state it differently. If R is a negative value, that means it's negatively correlated. They correlate with each other negatively. It is a dropping line. If the value of R is positive, if it is a value greater than 0, then it's positively correlated. And closer it is to +1, the stronger. All right. The stronger is the relationship in the positive direction. The closer the value of R is to -1, it's going to be a strong correlation negatively, but negatively. All right. So as you will note that this negative and positive one, uh, whether it's negative or rather whether R is a negative value or a positive value, kind of relates with the value of a slope. We said that if a slope is a negative value, then the line drops. If the slope is a positive value, then the line is a rising line. So we will see that later on, and also in chapter 15 when we go into inferential study, that R is also, it corresponds to the slope in our equation, right? Now that we have an understanding of what linear correlation coefficient is about, let's look at the formula to calculate the R value, right? Now this is the defining formula here. Like any other metrics, we have two sets of formulas. One is the defining formula and the other one is the computing formula. Computing formula is far more efficient. So when you do the calculations on your test exams under time constraints, I will have you use the what is it, the computing formula. All right, so make sure you are familiar with the computing formula and have practiced using it when preparing for the tests. All right. So the formula, the defining formula for R is 1 divided by n minus 1, so sample size minus 1, and then the covariance, so sigma x sub I minus x bar and y sub I minus y bar, which are the which are the means of all the x values and the means of all the y values, and we are subtracting them from the individual x values and the individual y values, and the results are being multiplied. All right, and then we are summing it. So we'll go through an exercise of this calculation. In the denominator, we have s sub x times s sub y. And what are they? They denote the sample standard deviations of the x values and the y values respectively. All right. So this is the defining formula to find the correlation coefficient. Let's walk through this simple example of finding the linear correlation coefficient using the defining formula, right? So we're going to work through this table here. But before I begin, let's just write the formula for R. Okay, so the formula is R equals 1 divided by n minus 1, and then we have sigma x minus x bar squared times y minus y bar squared. Y bar, oh, there's a square, and then the whole thing divided by s sub x times s sub y. Now, what is s sub x and s sub y? S sub x and s sub y are the standard deviations of the x values as well as the y values respectively. All right. So we have to find the standard deviation for all the x values and the y values. In addition, we also have to find the mean of all the x values as well as the y values, right? So let's go about doing it. The formula for the standard deviation is given here. To find the standard deviation of x, it's square root over sigma times sigma x minus x bar whole squared divided by n minus 1. This is the defining formula for any standard deviation. All right, this was taught in statistics 1 when we were working on the descriptive measures. Along with mean, we talked about variance and standard deviation. This was the formula we were taught to find standard deviations with. The defining formula, there is a corresponding computing formula as well. But since we are working with the defining formula to find R, we are going to use the defining formula to find the standard deviation as well. And for the standard deviation of Y, is the same formula except we replace X with a Y in the formula. Okay, so we do need to find X bar and Y bar, and then we need to find their standard deviations as well. So let's go about doing that. We're going to work through the table here. So let's start with X bar. Now I'm going to fix something here. The bars didn't come up too well in the PowerPoint. So I'm going to put the bars over the X's in this table first. Okay, so what is X bar? Keep in mind X bar goes with the formula sigma x, the sum of all the x values divided by the number of values we have, n, right? The sample size. So you have to sum up all your x values, which is 3 plus 2 plus 1, which is 6. So it's going to be 6 divided by n is 3. Therefore, we'll have an x bar value of 2, correct? And that's what we have here. Note that x bar equals 2. All right. And what we do here is in this column, in the third column, we subtract the x bar value from each of these individual x values. So 1 minus 2 is negative 1, 2 minus 2 is 0, 3 minus 2 is a 1, and that's how we got our values in the third column. For the fourth column, which is y minus y bar, we of course have to find y bar first. So it's the same process. It's going to be sigma y over n this time. So let's do that. So y bar is going to be sigma y over n, and sigma y is 3 plus 1, 4 plus 5, 9. So 9 divided by 3. So we'll have a y bar value of 3. So x bar equals 2 and y bar equals 3. All right. So let's just box this so we can look this up easily. So in the fourth column, we've taken each individual y values, and from them we've subtracted this value 3. Let me make it a little visible. Y bar equals 3, right? From the computation of the sample, from the computation of the mean of y. So this time 3 minus 3 is a 0, 1 minus 3 is a negative 2, 5 minus 3 is a positive 2. So we've completed the calculations in these two columns, the next column is x minus x bar multiplied by y minus y bar. In other words, we are just multiplying the third column and the fourth column. So -1 times 0 is a 0, 0 times -2 is a 0, and 1 times 2 is a 2. And then we sum up the values in this column, and 0 plus 0 plus 2 is a 2. So what this represents is sigma x minus x bar times y minus y bar, which we have in the formula to calculate R. All right, so that is what this 2 is, the sum of the fifth column here. Now, in this last but one column, we have x minus x bar squared. Now, we need to find this in order to calculate the standard deviation for x, right? The standard deviation formula has sigma x minus x bar squared. So, if we can find x minus x bar squared individually and then sum them up, we will have the numerator value for this s sub x. So, what we've done here is we've squared all the values in the third column. So -1 whole squared is a +1. 0 squared is a 0, and +1 squared is a 1. All right, and then we sum them up, and that gives us the sum of x minus x bar squared. And likewise, in the last column, we have squared all our y minus y bar values in the fourth column. So 0 squared is a 0, -2 whole squared is a +4, and 2 squared is a 4. Sum them up and we get our sigma y minus y bar squared. Okay, so now that we have all the values we need, let's calculate s sub x. So s sub x goes with this formula here. I'm going to write it, is equal to square root over, now sigma x minus x bar squared is a 2, correct? This is 2, so I'm going to write 2. And let me show you, because let me pull up my pointer here to show you where I'm pulling my, hold on one second. I'm having some technical difficulties pulling up my pointer here. Okay, now I got it. So this 2, sigma x minus x bar squared, is obtained from this value here. The sum of x minus x bar squared is a 2. That's how I got that 2 from. And n minus 1, n is 3, right? Is 3. So 3 minus 1 is a 2. So I'm going to write square root over 2 over 2, which is square root over 1. And therefore, we have an s sub x value of 1. Right? So I'm going to write s sub x equal to 1. And let me box that, because we are going to use this value in the denominator of the formula for R. S sub y, you pick your value of sigma y minus y squared. So let's write that down here. It's sigma. So 8 is the numerator, and then n minus 1 is 3 minus 1, therefore 2. So we have square root over 4, which is a 2. All right, so our s sub y value, s sub y is equal to 2. And again, let me box that. Okay, so now let's work on the formula for R. So 1 divided by n minus 1 is 1/2. All right, so it's going to be equal to 1/2. And then sigma x minus x bar squared. Okay, I'm sorry. I need to fix this formula here. So please excuse me. There is no square here. I don't know where I got that from. My mistake. Apologize. So it's sigma x minus x bar times y minus y bar. All right, no square in the formula for R. All right, so sigma x minus x bar times y minus y bar is this value here in this fifth column, this column here. So it's going to be times this whole bracket is going to be replaced by 2. All right, by 2. And then in the denominator, we are going to have s sub x, which is a 1, multiplied by s sub y, here, s sub y, which is a 2. So 1 times 2 is a 2. So we have half times 2, all right? 2 and 2 divide, which gives us a 1. All right, so we have 1 in the numerator, and 1 times 2 is, this is not 1.2. Keep in mind, this is a multiplication. So half, and therefore we have an R value of 0.5. All right, so this is how we go about calculating the linear correlation coefficient using the defining formula. Again, it's definitely more work, especially if you're working with a lot of large volume of x and y values. All right, if your n is large, then this is going to be more time consuming um, uh, than the computing formula is what I mean to say. All right. Here's the computing formula to calculate R, the linear correlation coefficient, uh, which is sigma x times y minus sigma x times sigma y divided by n. That's the numerator, and then in the denominator we have square root over sigma x squared minus sigma x squared, sigma x whole squared divided by n, multiplied by sigma y squared minus sigma y whole squared divided by n. All right, so we're going to work on a problem to use the computing formula as well. Now, let's go into a summary of the two formulas, and then we will go into a calculation using the computing formula. Now here are both the defining and the computing formula together in a single slide. Again, for the first one is the defining formula, which we just worked through as in an example. 1 divided by n minus 1 times sigma x sub I minus x bar times y sub I minus y bar. And keep in mind there's no square in this defining formula, right? When I worked out that example by mistake, I had put in a square. But that was wrong. All right, please make sure that you do not put a square in the defining formula if you're using that. Divided by s sub x and times s sub y, where s sub x and s sub y are the standard deviations of the x values and the y values respectively. And then the computing formula is the same thing, same as the defining formula, except that we use a faster way of doing the calculations, all right, using fewer columns. So we don't go about taking each individual x values and subtracting from it the means of the x and the y values, which can be time consuming if we are working with a large data sample. So in those cases, the computing formula is far more efficient. So let's work through a problem using the computing formula on that Orionic car example here. So as you will note in the computing formula, we have x times y, x multiplied by y, which is summed up. So we will need a column to multiply x, each individual x and y values, and sum them up. And that's what we have here in the third column. All right, the first column represents all the x values, the second column all the y values, which comes from the data given to us, not need any calculation. This is actual raw data that was provided to us, from which we also uh, calculated, or we came up with our regression equation. In the third column, to calculate our R, we have to just multiply x times y, because that's the first term of the numerator in our formula, in our computing formula. All right. So here we did 5 times 85, 425, 4 times 103, 412. So we go about multiplying each x and y value, the its related y value, and then we sum them up, which is 4732. All right. Now over here in the second term of the numerator, we have sigma x. That means sum of all the x values. So we do need to sum up our x column, and we came up with 58, right? And then also sigma y. So we have to sum up all our y values as well, which gave us 975. And in the formula, we'll eventually have to multiply these two and divide it by our sample size, which in this case is 11. All right. And then in the denominator, we first have to do sigma x squared minus sigma x sub I whole square divided by n. This is the computing formula for standard deviations. All right. So so that's what it is. You should be familiar uh, with this from uh, the chapter on standard deviations. And the same thing for y, to calculate the standard deviation of y, and then we multiply them, and then we take its square root at once. Okay, so for these x squared values and y squared values, we will need to square all our x values and sum them up, which is 326, and then all our y values will also need to be squared in this last column. That's what we did, and sum them up. All right, so let's now go in and plug our values into the formula. Okay, so just give me a minute while I pull up my worksheet here. Okay, so sigma x times y is this value here, 4732. So R equals, I'm just filling in the values of the terms in the numerator. Sigma x times y, 4732, which comes from here, and then there's a minus sign. So minus sigma x times sigma y. So what is sigma x? Is 58, and I'm going to surround this with brackets. All right, so 58 multiplied by sigma y, which is 975 divided by n is 11. So let's write the 11, and now we will write the expression in the denominator. So sigma x squared, right? So sigma x squared is all the x squared values summed up, 326. So I'm going to put here 326 minus sigma x whole squared is 58 squared. 58 squared divided by 11. All right, so that's the first box, multiplied by sigma y squared. So sigma y squared is here 96129. Let's write that, 96,129 minus sigma y whole squared is 975 squared divided by 11. Okay, and when you do this calculation, you should come up with a value of negative, all right, the numerator should give you a value of negative 408.91. That's the numerator, and the denominator, after you take the square root and everything, should give you 42, sorry, 442.63 for an R value of negative 0.924. So R equals negative 0.924. Okay, so keep in mind, let's just go over what we found here. R for this problem. R is negative 0.924, and this negative sign means that this x and y variables are negatively correlated. That means as x increases, the y values decrease. That's what it means. Okay, so this tells us we are trying to interpret our R value. It tells us it's negatively correlated, and that negative sign on that R value tells us it's negatively correlated. And the other one is it's a strong correlation. Remember, R tells us the correlation coefficient tells us how strongly as well as in which direction, the strength and the direction of the correlation. All right. So it's strongly related, correlated. And how do we know that? Because this value is closer to negative 1. All right. The closer the R value is to negative 1, or if it's a positive value to positive 1, that means stronger is the correlation. Okay. So that's how you use the computing formula to calculate your R value. Now this chart is showing graphically the correlation. In the case of positive correlation, we have a line rising. This is a rising line from left to right, and you see all the actual values, all the values lie on the line, and that's a perfect positive linear correlation. In this case, the value of R is going to be equal to 1. It's a strong, very strong, rather a perfect positive linear correlation. However, this is going to be very rarely will this case happen, especially in the actual world. All right, but this is the ideal situation, but it's not realistic. For B, it shows strong positive linear correlation. R equals 0.9, as in the case of the Orion data. It was R was 0.92, so it was very strong positive correlation because it's close to 1. And it's positive because it's a rising line, but you see that it's less than perfect because there are some data points that are not on the line. Yes, okay, some data points are a little bit off, falling off the line. If none of or very few of the data points lie on the line, that means it's a weak positive linear correlation. It's positive, all right, because it's still a rising line, but the data points are nowhere near the or nowhere on the line. It's off from the line. So this R value is 0.4. All right, it's away from negative 1 or positive 1 at both ends. Okay, here are some graphical representations of a perfect negative linear correlation. In this case, R equals negative 1. Whenever we have a dropping line, a falling line, R has to be negative. Uh, E is a case of strong negative linear correlation. R equals negative 0.9. In fact, this was the case in our Orion example, not the first one. The Orion example, R was negative 0.92, not positive. If I said previously this was the case, no. All right. It was a case of negative linear correlation. And then for F, it's weak negative linear correlation because you see none of the actual data points lie on the line. And finally, here we have a case where r equals 0, so there's no linear correlation going on here. Okay, they are not at all correlated. In fact, x and y have nothing to do with each other. They are not influencing, x is not influencing y at all. That's what it means. And at the end, let's look at the relationship between coefficient of determination and the correlation coefficient. We saw that the notation for the coefficient of determination was r squared, and that of the linear correlation coefficient was r. So does that mean that if you find your r value, can you simply square it and get your coefficient of determination? Yes, you can. All right, you can. Once you know your r value, then you can just square your r value to come up with the coefficient of determination if you've calculated the r value correctly. All right. However, it's risky to change, or rather it's risky to derive the uh, r value from the r squared value by taking the square root of r squared. All right, because it's when you take the square root of r squared, you will get the correct absolute value probably, but you won't know whether it's going to be positively correlated or negatively correlated, because you will have a plus minus whatever square root of r squared calculates to, and you will be in a dilemma whether it's a positive correlation or a negative correlation, right? So you can, if you're given an r value, it's safe to square it and find the coefficient of determination without having to calculate coefficient of determination separately uh, through the formula. But if you're given r squared, it's risky to just find its square root to get the r value, because you will not necessarily know what sign to apply, whether it's a negative correlation or a positive correlation. All right, so this brings us to the end of chapter 14. It was a pretty long chapter, because just because this study is a little bit different from the types of study in statistics that we have learned before. Now, chapter 15 is on inferential statistics, inferential part of regression and correlation, this chapter. All right, so we will start with that, and that's going to be the last chapter in our syllabus for this course.